So, good afternoon to everybody. I'm Michele Lombardi from University of Bologna. I'm going to be the chair for this section on application. The first talk is titled Learning Surrogate Function for the Short Horizon Planning in Same-Day Delivery Problems. And I think we can start. A signal when we have, it's a video, so there shouldn't be really a problem with timing.
Hello everyone, my name is Adrian Bracher. I'm a student at the Technical University of Vienna, and what I'm about to present is what evolved out of my bachelor's thesis. And my supervisors were Nikolaus Frohner and Günther Raidl. I'm sure most of you have ordered products online before, and if you have, you may have noticed a trend towards ever decreasing delivery times. Online retailers sometimes go as far as promising delivery only hours after an order is placed. And they do this for multiple reasons, but the most common is to attract more customers. Offering such short-term delivery can be quite challenging, and labor and cost-effective vehicle routing is a necessity when trying to get it right. Same-day delivery problems are stochastic and dynamic vehicle routing problems with an additional focus on very short delivery times. Like with all vehicle routing problems, orders have to be combined to form routes, and they also have to be combined in a way that optimizes certain criteria, for example, cost. Here you can see one such route. So the concrete problem that we're trying to solve in our studies is a same-day delivery problem variant where orders arrive dynamically over the day and are due only 1 to 2 hours after arrival. Whenever a new order arrives, it triggers a new optimization based on the new situation, which leaves us only very short times to conclude our optimization and derive a solution. We're also given stochastic information about the day, for example, expected order numbers. So how exactly do our instances look like? We're given drivers with their shift times. We have orders and their locations. And for each order, we also get an availability time, which is the time that the order was placed, and a due time, which is the time that the order has to be delivered. All deliveries past that time have a tardiness, and that's what we want to avoid. We're also given travel times to and from each order location, also including the warehouse location. In addition to what I've already mentioned, we are also given the previously mentioned stochastic information. For example, the number of orders within a given time interval, and an estimate on how long it takes on average to deliver one order. Now that we know that we're supposed to construct routes and now that we know that we have to construct routes, we have to clarify what we want to achieve with those routes. And our utmost objective is to avoid tardiness as much as possible. But if it's unavoidable, then we at least want to balance it over the orders. The secondary objective is to minimize the total route duration, which can also be understood as the total active labor time of our drivers. Given these objectives and the problem statement, my colleagues decided to use adaptive large neighborhood search, which is a common meta heuristic and has been applied to the stochastic and dynamic vehicle routing problem in previous papers. And the first variant of this adaptive large neighborhood search only considered currently available orders in the routing, which is why we declare it myopic. And it also didn't look into the future and try to adapt the routes for for future orders. This was a problem, as we discovered soon, and you can see the upper two routes here. are part of a solution and are actually consecutive points in time, where you can see that the myopic solution, which is shown above, places orders 1 to 5 and the order 6 in the same route, even though order 6 is due very far in the future, and orders 1 to 5 are due very soon, and also they are spatially separated, as you can see. And the result of that is that half an hour later, when orders 7 to 10 arrive, which would be spatially and also temporally similar to order 6, the order 6 cannot be included anymore, since the previous route has already been started, because otherwise orders 1 to 5 would have been delivered late. And the optimal solution here is to split the first route into orders 1 to 5 and order 6. And then this allows us that because order 6 is due very late, we can use it 30 minutes later and start this route would be started very late. So half an hour later, it's still not started yet. And it can be rescheduled to form this second route that you can see here. And overall, it's an improved solution. So what do we have to do to consider these problems and improve our solution or our algorithm? Well, we have to use the stochastic information given to us and adapt our routes for upcoming orders. So what we did next was look into the literature, and we found mostly sampling-based approaches. They are usually used by sampling orders, which are then combined to scenarios. These are solved independently, and the solution to these scenarios are then combined to have a solution to the actual problem via a consensus method. The major problem with this is that for our near real-time dynamic optimization, this is too slow, since a lot of scenarios have to be solved to make meaningful predictions. And yeah, it's also, and it's also more complicated since the samples have been added. So instead of using sampling-based techniques in the actual runs, we use sampling-based techniques beforehand to generate training data, and then use that generated training data to fit models, which are then used to consider future improvements of route durations. To further clarify this approach, we made these activity diagrams. And as you can see in the offline training phase, we use sampling to generate training data, which is then used to fit models. And those fitted models are then used in the objective function of our adaptive large neighborhood search to produce overall improved solutions. So since we're training models, we have features. And the most important ones are the myopic route duration. So the route duration only considering currently available orders, how many orders there are in the route, the time of optimization, the planned departure time, and probably most importantly, how many orders we can expect, or we can expect before the route is started. And we also have that notion of an estimate of how long it takes on average to deliver one order. This is included since it helps us to distinguish between good and bad routes. Here you can see a formalization of the aforementioned surrogate function. The surrogate function actually replaces the myopic route duration. And most important on this slide is that only routes that have a worse than average mean order duration are considered for discounting. All other better routes are left the way they are, and yeah, the myopic route duration is used. So we tried three different models to realize this surrogate function. And the first one is a handcrafted exponential function, motivated by the assumption that given enough time, all routes approach this average order duration. And of course, the less time left, the less improvement to expect, which is why we model this here with exponential decay. We also tried a linear regression and a fully connected multi-layer perceptron. There was one more improvement that we've done to our algorithm and that we have only implemented fairly recently, which is bootstrapping. We don't use the fitted model that was trained with the sampling generated training data anymore, but instead we use that model to create another iteration of training data, which is then used to create another new models that are then used in the adaptive large neighborhood search. This seems a bit pointless, but it in practice it helped us to eliminate skew in the training data, and the results showed that it was quite effective. Now on to our computational study. We created 240 instances in total with 12 different instance classes. They differ in the average number of orders per hour, which is in the range of 10 to 60, and also how these orders per hour are distributed over the whole day. We also call these orders per hour load. The three load distribution patterns are steady, rising, and falling over the whole day. We compare ourselves or our approaches with a sampling-based approach with 100 scenarios and samples generated for up to 1 hour into the future. What you can see here is multiple box plots showing the improvement over the myopic solutions. And you can see that we had up to 10% improvement in the median. You can also see that for loads 10 and 20, sampling performs quite similar to our approaches. And yeah, for higher loads, we couldn't compute sampling results since it just took too long. And that's where the major advantage of our approaches is. Yeah, you can also see that a higher load or more orders per hour is beneficial to the performance, which kind of makes sense, since if you have more orders to improve your route, then yeah, it does make sense. Yeah, here we picked out the results for average load 20. And this is the highest load that we could compute classical or sampling solutions. And you can see that the results are pretty similar. The improvement is pretty similar, but the runtime is reduced by orders of magnitude, as you can see here. Here we have a comparison of the bootstrapping models with the non-bootstrapping models. EXP means exponential, LR is linear regression, MLP is the multi-layer perceptron, of course, and the ones with -BS mean the bootstrapping versions of these. And you can see an improvement of up to 2.5%, again, relative to the myopic solutions. Yeah. So in conclusion, what I've presented here is an alternative to sampling for considering stochastic information. And we've seen up to 10% improvement in the median. We see that our approaches perform especially well for higher load situations. And of the three models, the exponential function seems to perform the best. We assume that that is due to it being the most robust to biases in the training data. We've listed here three topics future work that we can imagine. And one is to eliminate the bias in the training data and hopefully boost the performance of the linear regression and multi-layer perceptron. Another is that this estimate of the mean order duration is constant over the whole day, and that doesn't really that isn't really realistic, because due to traffic and load changes, it is of course not constant, and that would be interesting to consider as well. And third is that we want to try or test on different instances. Real world data would be very interesting, and also the idea of clustered orders is interesting to us. Okay, thank you for your attention, and I'm happy to answer all your questions.
Yep, many thanks for the presentation, which was very interesting and also perfect on time. And there's time for a few questions. Either from the audience or online. So there's one by Peter.
I'm wondering if you've thought about, particularly for the exponential, which doesn't have that many parameters, that you could actually run the actual optimization problem and train through the optimization problem, right? Because what you're trying to do is get that 10% benefit. So have you thought about trying that?
I'm not sure if I get the question. Could you repeat that?
So you can sort of do grid search if you want on the exponential function, and take the resulting function that you built for that grid search, run it through, run some samples, see how much value you got, go back and do it again, right? So you can actually use the optimization function itself to work out the value, rather than just post-processing it, post-evaluating it.
Yeah, there's actually only one parameter in the exponential function, and we've actually thought about like just running something like grid search CV. Yeah, that would be interesting. We didn't do it in the end, but it seems like another good idea to improve on this.
So I agree that what Peter suggested is very interesting. It will draw some kind of connection between the approach that you are currently having and what is done, for example, in predict then optimize. Also, another connection that comes to my mind is with a paper on the kidney exchange, online kidney exchange problem, which was making use of something called weighted myopia. And is there other question either in the room or online? Otherwise, I have some.
There are no questions in the room at this time.
Okay, then just a conjecture. So I worked in the past with approaches that embed machine learning model inside decision-making models. And one issue that we encountered was that sometimes if you have weaknesses in the machine learning model, you end up having suboptimal solutions because they are misleading the solver. So did that happen in your case? Do you think that the loop that you introduced at the end with the training, with the generation of the training instances, is maybe working because of this kind of thing?
I'm not sure if I get the question. I'm sorry.
Sometimes when you pre-train a model like you do, it ends up being weak in certain areas of the search space.
Okay.
And that can then mislead the solver. The kind of training that you added at the end, where you generate training instances using the solver itself, has a chance of countering this kind of phenomenon. Did you make an analysis to test this?
No, we did not. I don't know if my supervisors want to say anything to that, but I don't really have an answer to that question, honestly. I don't think we have considered that.
So if you haven't done that, then it may be worth a look. So it may give you provide you some motivation for why the second training scheme that you tested is improving.
Okay, thank you.
Okay, thanks again.